first concept that you'd need for the first chapter, real numbers, for it solving exercise 1.1 is Euclid's division lemma. Euclid's division lemma states that for any two integers a and b, there exists q and r such that a is equal to bq plus r. Now this might look hard at first, but if you think about it, we do this in our day-to-day math. Where do we do this? You might ask. Simple. Suppose we're dividing two numbers 12 and 4. We get, if we do the traditional method, we get 12, 4, 3, 12, 0. That's basically it. Let a equals to 12 and b equal to 4. Therefore the quotient would be 3 and the remainder would be 0. That's basically what we did. A is equal to bq plus r. So Euclid basically written division in a statement form. So I hope it's clear. But what else would you notice after dividing is that the remainder can either be equal to 0 or less than or greater than 0, and it will always be less than the divisor. As we can see, the remainder in this case is either 0, it is 0, however it's less than 4. So this is the second part. Basically a is equal to bq plus r such that 0 is less than equal to r less than b. Now using Euclid's division lemma, we can do the first type of question, which is finding HCF of two numbers, which is to find the HCF. Now to find the HCF, we can take two numbers. Let's take the first question of the first exercise, which is 135 and 225. The first pair of numbers is 135 and 225. To find the HCF of these two numbers, write down the lemma first. A is equal to bq plus r. So we here write down the larger number as a. Therefore 225 is a and b is the smaller number, which is 135. And now we use simple division. 135 into 1 plus 90. Furthermore, 135, now take the b term and write it down as a. Take the r term and write it down as b. So this would be 90 into 1 plus 45. Now we keep doing this until our remainder will become 0 to find the HCF. This gives us 135 is equal to, this gives us 90 is equal to 45 into 2 plus 0. Therefore the HCF becomes the b term, which is what? 45. That's how we use Euclid's division lemma to find the HCF of a pair of numbers. And now the second concept we'd need for the first to solve the first exercise with ease is using Euclid's division lemma to manipulate. Now we can do so by taking the example of the last question of the first exercise, which is to use question number 5, to use Euclid's division lemma. Use Euclid's division lemma to show that the cube of any positive integer is of the form 9m plus 1 or 9m plus 8. Now we can do this in three cases. And first step is, since they said the cube, if they said cube, therefore we can assume b to be 3. If they were to say squared, then it'd be b to be 2. So you have to assume b to be 3 as they said cube. So a is equal to 3q plus r. However, what else did we add? 0 is less than equal to r less than b. Therefore r can be either 0, 1, 2. So continuing from this, they said the cube of any positive integer. So therefore the positive integer would be a. So a cube, and in case 1, there are three cases. So case 1 would be where r equal to 0. So a cube is equal to 3q, the whole cube, because we're cubing on both sides. This gives us 27q cube. By taking 9 out common, we get 3q cube. Now here is the manipulating part. Let 3q cube equals to m. Therefore a cube is equal to 9m. Thus we solve the first part. Now for case 2, since there are 3 cases, r equals to 1, in which case a cube is equal to 3q plus 1 the whole cube. Now we know the a plus b the whole cube formula is a cube plus b cube plus 3ab into a plus b. This gives us 27q cube plus 1 cube is 1 plus 9q into 3q plus 1. By simplifying even more, we get 27q cube plus 27q squared plus 9q plus 1. Now the manipulation part again would be take 9 out common. This would give us 3q cube plus 3q square plus q plus 1. Now let 3q cube plus 3q square plus q equal to m. This would give us 9m plus 1. Now similarly, in the case 3, if we were to take case 3, it would be nothing but case 3 would be nothing but a cube is equal to 3q plus 2 the whole cube. And simplifying using a plus b identity, which is mentioned over here, a cube plus b cube plus 3ab into a plus b, we could find it. Thus we proved that a cube is equal to 9m plus 1 or 9m plus 2. However, we can't go, if you're still wondering why we can't go to r is equal to 3, that's because we have 0 is less than equal to r less than b, and we assume b to be 3. Hope you guys understood.